Yeah, good afternoon, everyone. My name is Saketh Sridhara, and I started this fall as an assistant professor at the University of Massachusetts in Amherst. First off, thanks to Faiz, Jitesh, and the organizers of this workshop. It's great to meet you all. Kind of jumping in quickly into my research interests. So let's look at the design of mechanical systems and take a broad view at this topic and jump into kind of the preliminary and the detailed design phases. You want to optimize for the geometry of various parts that go into, for example, a car. And also, what goes into engineering design is a lot of data. For example, data of springs, screws, fasteners, bearings, and so on. And if you look at the average distribution, about 20% of the parts that go into a car are these kind of continuous geometries. A car typically has about 30,000 parts, and out of that, about 25,000 parts come from catalogs, which are typically these repositories of engineering data. They're discrete, high-dimensional. Most of the area of geometry optimization is well studied in size, shape, and topology optimization. So I set out asking the question, how do we actually integrate this space? Because if we were to go away from single component design, as we've talked earlier today in a couple of sessions, we really have to look at designing engineering systems. And for that, we need to incorporate a lot of engineering data. So here are a couple of examples of the said engineering data, some familiar ones. For example, a catalog of screws from Shigley's Mechanical Engineering Design Handbook, or a catalog of materials that you would choose from one of Ashby's books. So the typical challenges from these kind of tabular representations, if you can call them, are that it is difficult to kind of stare at these handbooks, which is kind of the standard for design engineers, to identify gaps to innovate, where do I offer new products, and also to identify errors. And you'd be surprised at the number of errors that have creeped into these catalogs and are kind of legacy in the design handbook. So it's kind of difficult to explore. And when it comes to users of these catalogs, the design engineers who are designing systems, they need to optimally kind of select from these and use it. For example, you want to select the best material. Or if you want to replace the material with some other material, you need to look at substitutes. And this tabular format is not really amenable for continuous optimization. So here is one of the approaches that I'm pursuing. So geometry optimization, continuous design variables, well studied. What we set out to do is we look at such engineering catalogs and generate a continuous representation of them, a continuous analog. Neural networks are good at doing this, but you could employ other methods that could fit data. And now with both these spaces being continuous, you can now target the optimization beyond components. You can target optimization of assemblies, systems, and then you can penalize in this space, in this continuous space, to move towards discrete designs. I'll not go into the details of the architecture because that's not too important, but what I would emphasize over here is we use some kinds of neural networks that essentially do dimension reduction, and variational autoencoders generalize nonlinear PCAs. So you could use something like that to generate a low-dimensional representation of a high-dimensional material database as shown over here. And we also show that these kind of generalized Ashby's charts. Ashby's charts represent material properties in 2 dimensions, whereas these can be viewed as Ashby's charts when you have multiple attributes and you reduce that to a low dimension, like materials grouped together. The materials that are far apart are distinct, and some are even outliers, for example. So this is what the new representation that we look at to navigate such catalogs. And as it's been discussed, it's good to kind of take these methods to design engineers who actually use these methods to design products. In my PhD, we went to Milwaukee Tool, and we gave them this visual representation and asked them, please go ahead and see if you can make some use of this. And they were able to kind of look at the functionality, and they said it's useful to look at catalogs visually because humans are visual thinkers. But then many questions remain to be answered. That is, what do the latent access mean, and how effectively can design engineers use these novel representations to make selections? And this came out earlier this year in the Journal of Mechanical Design on how we can use this neural networks to visualize catalogs. I'm not going to go into detail here about using neural networks to represent geometries for topology optimization. Some of you in the audience have worked with these methods, but I would specifically focus on a couple of things that recently have been coming out in the papers, that neural networks can tend to find better local minima for non-compliance problems. For example, me with Adi here in the audience, we worked on a problem where we used neural networks and we were able to find better designs for negative Poisson's ratio problems. So the jury is out if it is going to solve all problems better, but there are some problems that neural networks can find better solutions when we use it to represent geometry. So just wanted to briefly mention that. And this is kind of the template of how we would integrate continuous and discrete design variables shown in this figure over here. We can continue to use density-based methods to do your topology optimization of the geometry, and then you can bring in this continuous representation of catalogs to kind of say, for example, in this case, select the material, and finally you can iterate through gradient-based optimization and then penalize the distances of the material location to go snap towards real material. So this is kind of a template of how we can integrate discrete catalogs with continuous geometries. So to summarize what I've been developing is, I would say you can look at this as a paradigm shift of how engineering catalogs can be now converted to like a continuous representation, and this can be used for the design of mechanical assemblies and systems going forward. Also of interest are differentiable physics solvers that enable you to get sensitivity information, and that's gaining good traction in the field. Also, the representations of geometries using neural networks can find better local minima sometimes, but it's good to kind of experiment with traditional and emerging methods. And this kind of is what leads to more complicated and more real-world problems of design optimization, in my opinion. To conclude, I think that design of mechanical systems, the moment you move away from components, necessarily needs you to look at data. The data can be from catalogs that help you kind of navigate what is the best choice that you have to make to design this mechanical system. Machine learning approaches, I marked there, underlined 8 design engineers. I believe we still need design engineers to make decisions and own those decisions, but these approaches can aid engineers to visualize these catalogs and also optimize and kind of make better choices with them. And this I see as the pathway. We have done well in designing mechanical components, topology optimization. We really have to move towards designing assemblies and hopefully in the near future go towards designing entire engineered systems. Along the way, taking user feedback is critical. We need to ensure that the generated or the methods that we use are as reliable as the rules that have been passed down through experience. So we need to understand what these methods really mean and also gain the trust of these methods so that design engineers can actually adopt them. And going along the discussions of the morning, we need to make sure that use of machine learning methods meet the break-even thresholds, that doing it using traditional methods, if it's going to be faster for a certain problem, we should still stick to those methods while establishing that the proposed methods can actually meet those benchmarks or even exceed them. So thank you for your patience, and that's my email ID if you want to reach out. Yeah.
Right, questions? Can you elaborate like what kind of design process or for what type of example this will be useful? Because when you showed the tables, I thought of like simply automating a lookup table or things like that might be useful for discrete data.
Yeah. So when you have to kind of select from these components, looking up can, if you were to brute force through all the possible choices, lookup tables can help. But sometimes the choices of materials, for example, can run into hundreds of thousands. And then you do not want to evaluate all possible combinations of these. So that's where some of this continuous frameworks will come in to help. You can search the space much faster with the continuous equivalent. Yeah.
Thanks.
Right. Yeah.
Thank you, Saketh. Very interesting presentation. So the regions in, let's say, the Ashby space, let's call it like that, may not be contiguous, right?
Mm-hmm.
How do you make sure that the optimization doesn't get stuck in one of those regions and doesn't find, another region that might be better?
Yeah, that's a good question. So there are local minima in the latent space or the low dimensional space that you construct. There are two ways to circumvent that. One is multi-start methods, maybe search different spaces in the latent space. You would still be doing better than brute force evaluation of all the possible candidates. And second is you can use a momentum-based search. Even though it's gradient-based, you can add in some momentum to make sure that, if you're stuck in a local minima, it's going to try to push it out for a bit. And if it can jump over to something better, then that momentum will ensure that it's not trapped in a very small local minima. So even if you're in a local minima, it's a pretty deep valley to be in. Yeah. So there are a couple of optimization-based answers to kind of come out of that issue. Yeah.
Thank you.
Thank you.
Thank you. It was a fascinating talk. When you do the search in the latent space of these discrete elements and you optimize it, let's say, isn't there a danger when you decode that you get a decoded product that doesn't exist in your catalog? Like, how do you reconcile that? Is that like a nearest neighbor pickup, or what are the methods there?
Yeah, so we actually looked at some of those approaches. So one thing is, yes, when we were looking at material properties, we kind of decoded it, and sometimes it was not like a realistic material that was coming out, at which case snapping to the nearest available material or the nearest neighbor, maybe k equal to 3 or something like that. We also came up with like a confidence metric to say that if it's close to a material, just like most machine learning methods, if you're close to a real discrete value, then the value is kind of realistic to you. And if you're somewhat in no man's land, we came up with the confidence metric saying that, okay, this result is of low confidence, so you kind of have to test the k nearest neighbors to make sure that it actually meets your constraints, and then you kind of re-optimize for the geometry. So that kind of takes it to a two-step process, but that would still be, I would say, more efficient than trying to brute force through the alternatives that are available discretely. Yeah.
Awesome, great. Let's thank our last speaker. Thank you, Saketh.
Thank you.